Hello friends. Today we will solve some problems based on heat transfer. We are taking three problems based on heat transfer. One problem is decent, but two problems are good problems based on heat transfer. Let's see question number one. A copper rod initially at room temperature 20 degrees centigrade. And at T equals to 0, the whole rod, which you are seeing here, they are at 20 degrees centigrade. Okay. Of non-uniform cross sections, the cross sectional area is not constant, which you are able to see here. Okay. Is placed between a steam chamber at 100 degrees centigrade. There is a steam chamber which is maintained at 100 degrees centigrade and an ice chamber which is maintained at 0 degrees centigrade. Fine. They are asking you basic questions. First question they are asking you the initial rate of heat flow dq by dt. It will be maximum at which sections, or it will be same at all sections. The steady state heat transfer in a dq by dt they are asking, and steady state temperature gradient they are asking, and steady state dt by dt they are asking at all points. See, first we'll answer the obvious part which you know, all know. At steady state, the rate of heat transfer will be same, will be constant throughout the sections. Yes or no? That means same at all sections. So answer B should be matched with the T. Okay. Now they're asking the steady state, this value dt by dt. So the meaning of steady state means they are not changing with respect to time. That means dt by dt must be equals to 0. But this we are writing at steady state. At steady state. Okay. So at every section it will be 0. That means we can say same at all sections. So D's answer will be T. Now second part we will try to answer. The steady state temperature gradient they are asking. So we know the Fourier's law of heat conduction. They say rate of heat transfer dq by dt, that is equals to minus Ka into dt by dx. Correct? So we are interested in temperature gradient. So we can write dt by dx. Obviously we know the temperature gradient will be negative because heat flows from higher temperature to lower temperature. This we can write q dot divided by K. This we can write, yes or no? Now if you see the q dot, already I said that is constant to all sections. Q dot is constant to all sections. Now K is also constant because same copper wire is there, sorry, copper material is there. So that is same. Area of section, if you see, that is variable, yes or no? So wherever area is minimum, at that point this temperature gradient okay, that is minus d by dx we are saying, that will be basically maximum. So where the area is minimum, so at section B area is minimum, so we can say temperature gradient will be maximum at temperature section B. So C's answer should be Q. Now if you see the first options, what they are saying, initial rate of heat transfer. These are important questions. That means they are trying to say do the unsteady state heat analysis. So what we know, let me give just a basic introduction of that part. Okay, let's say there is a small sections. The heat is coming here in Q dot in. This is Q dot out. Let's say the mass of this part M, specific heat is C. So and temperature at an instant of time is T. So we can write Q dot in minus Q dot out, that is equals to MC dt by dt. Okay. So that is basically the equation for unsteady state heat conductions. For unsteady state heat conduction, we can write these equations. This is heat conduction for unsteady state. Steady state. Okay. So once the steady state arrives, we know this term becomes 0. That means Q dot in equals to Q dot out, and that's what we are saying in the option 1. Okay. Now in this case, what we are trying to say, wherever this dt by dt will be maximum, okay, wherever temperature difference is maximum, the rate of heat transfer will be maximum at that locations. So now see, At section A, the temperature difference is how much? 100, and initial temperature was how much? 20. So this at section A, T equals to 0, T equals to 0. What is the value of dt? That is equals to 100 minus 20, that is 80 degrees centigrade. Similarly, at section B, you will say it is almost 0, dt equals to 0. At section C, if you observe, that is how much? There is 20 minus 0, it is 20. dt equals to 20. Wherever dt is more, the rate of heat transfer will be more, you can say radiant, okay? More faster rate of heat transfer there. So what we can say, at section A, rate of heat transfer is maximum as compared to section C, and at B, there will be least rate of heat transfer at T equals to 0. So what we can say, the initial rate of heat transfer will be maximum at section A. So A's answer will be P. A's answer should be B, P, B should be matched with the T, C should match with the Q, and D should match with the T. Let's see the answers what they have mentioned. A, they are trying to match with the P, our also is same. B, they are matching with the T, B is matching with the T, correct. C is Q and D is T, that's correct. I hope you understood this part. Let's see the question number 2. They are saying a well insulated, very good, this word you should be keep in mind. Box contains a water specific heat C, very good, and very large conductivity. What the meaning of this part is? Of mass m0 and temperature T0 at T equals to 0. Yani this container is well insulated. That means there cannot be any heat loss to the surrounding. Okay, it is an adiabatic wall kind of things. The second word they are trying to say, it is a very large conductivity. What does it mean? Large conductivity means everywhere the temperature of the water remains same. That is the meaning of large conductivity. If the heat is being added to it uniformly at a constant rate R, that means we are supplying the heat basically by any medium, and that rate is constant, that is R. Water is leaking out at it from the constant rate, dm by dt is given to you lambda. Okay, so they are asking temperature of the water at any instant of time. T should be less than m0 by lambda, they are trying to say. Okay, first let's try to say what is the mass of the water at any instant of time. Since dm by dt is constant, so can I say it is simply m0 minus lambda into T. That is the mass of the water at any instant of time. Okay. Now second step, what we'll do, whatever heat we are giving, whatever heat we are supplying, that is getting converted. We can write these things, ms dt by dt. Can we write? Not. This we can write ms dt by dt. Sorry, m0 minus lambda t. This should be m0 minus lambda t. My mistake. This should be m0 minus lambda into t. Not lambda naught, it is lambda. Okay. So this equation we can write. Now if you see, there are two variables. One is temperature, second is time. So we can easily integrate this part. So we can write dt, that is equals to R by C into m0, sorry, dt divided by m0 minus lambda t. Now we are integrating this part. At t equals to 0, the temperature is T0. At instant of time, temperature is T. So we can write here T minus T0, that is equals to R by C ln times of m0 minus lambda t. We have to divide by lambda with minus lambda basically, but we are changing the limit here. We are changing the limit from t to 0. Okay, this lambda is basically compensated. Minus this term is basically compensated. So this temperature at an instant of time, we are writing T0 plus R by lambda C ln times of m0 divided by m0 minus lambda t. So this is the temperature of the water at any instant of time. So the answer should be R by lambda C, correct, ln times of m0 minus lambda t plus T0. So second option is option B is matching basically with this part. Okay, I hope so you must have understood this part. It's a good questions based on energy conservations. Let's see question number 3. This is a growth of ice basically over a pond. Discussions. A lake surface is exposed to an atmosphere where the temperature is less than 0 degree centigrade. Fine. If the thickness of ice layer is formed on the surface that grows from 2 centimeter to 4 centimeter in 1 hour. Fine. The atmospheric temperature is given to you Ta. The conductivity of ice is given to you 4 into 10 minus 3 Kelvin per centimeter per second per degree centigrade, and density of ice is 0.9 gram per cc. Latent heat of fusion of ice is 80 calorie per gram. They are asking you few questions. Neglect the change of density of the state change and assume that water below the ice has temperature 0 degree centigrade everywhere. So what they are trying to say, this is a lake and the temperature of the lake is 0 degree centigrade. Here an ice has formed basically. And surrounding temperature they are saying Ta. This temperature everywhere is 0 degree centigrade and this is also 0 degree centigrade. So what we can say at any instant of time, let's say the thickness of the layer is x. Thickness of the ice which is formed is x. In the next interval of times, dx amount of ice further forms. Okay, this is a dx amount of ice forms. Now, whatever ice has formed, because of that heat will be released. That heat is being conducted to the, you can say, ice layer. So obviously at this temperature 0 degree centigrade, at this point it is contact with the atmosphere. So temperature of the ice will be Ta at the top surface. So what we are using here, we are using again energy equations. So rate of formation of ice, that is equals to dm into L divided by dt. That is the heat released due to the formation of ice, and that must be conducted to the basically ice, that is K of ice into A into delta T, that we can write 0 minus Ta divided by x. At any instant of time, this is x. Now what we can write dm? Dm is basically this mass. This mass we are saying dm. So what will dm? Density of ice which will form into specific heat of ice. Sorry, not density into volume, no? My mistake. Volume we can write area into dx. Let's write this part. So density of ice into area into dx by dt into latent heat of fusions, K of ice into area minus sign Ta by x. An interesting fact you will get here, this area get cancelled. What does it mean? Whether a small pond or big lake or anything is there, the rate of formation of ice must be same in all cases. Very good. Let's see this part, what happens. We can write x dx, that should be equals to minus of K ice into Ta divided by density of ice into latent heat of fusion into dt. Integrate. At t equals to 0, this was 2 centimeter. At t equals to 1 hour, they are saying it becomes 4 centimeter. It's a very simple integration now. This we can write basically 1 by 2 x square and 4 square minus 2 square. We are converting into meter, that is 10 to the power minus 2 into 10 to the minus 2. Okay? So that is everything converted into meter. That is K of ice will write here. What is K of ice? K of ice is given to you. The value of K of ice is given to you 4 into 10 to the minus 3. 4 into 10 to the minus 3. That's all. That is given to you calorie per second per degree centigrade. So no need to convert into meter. Let it be as centimeter only. Okay. So I'm not converting in this part. Into temperature of the atmosphere is Ta. Density of ice is given to you how much? Density of ice is 0.9 gram per cc. This we can write 0.9 gram per centimeter cube. multiplied by. What is the latent heat of fusion they are trying to say? That is 80 calorie per grams. So just multiply by 80. Now you just take the basic dimensions. This is in hours, so let me convert into second basically. That is basically 3600 second into 3600. Okay, so let's check the dimensions. Left hand side dimensions we said centimeter square. Right hand side dimension we are trying to write. Okay, so K of ice, what is the dimension they are writing, right? K of ice they are writing calorie per gram per second. Calorie, sorry, my mistake. Calorie per gram per second per degree centigrade. Correct? Okay. Density of ice they are trying to write gram per centimeter cube, and this also they are trying to write latent heat they are trying to write 80 calorie per gram. 80 calorie per gram. So this gram get cancelled. Check here. This gram get cancelled. This calorie also term also get cancelled. Okay, and yeah, fine. What else get cancelled? Centimeter cube was there here. It is basically calorie per this things. So this centimeter cube will go in the numerator, and some more centimeters should come in picture. No, where I'm missing? Wait a minute. No, seems everything is fine. Seems everything is fine. This is calorie per gram. So this is not. Achha, this second term get cancelled. This number of these things will get in degree centigrade. Okay, and this gram term also had to get cancelled already. Okay, because this gram and that gram will cancel out. So what left basically? Nothing is left basically. Okay, so that is our answer. So if you solve this part, this temperature directly will get basically in degree centigrade. So if you solve it, you will get this value comes out to be minus 30 degrees centigrade. So that arithmetic part I am not doing. You can check this dimension wala part again. Okay, thank you very much.